Now it's time for the first session and the oral contributions. And here is John Hearnshaw. Thank you very much, John, for being here. I know it's late there, so thank you very much. It's your time.
Late, Beatrice. It's 1 o'clock in the morning for me, but I'm still awake, but only just. So session 5 is starting now, and session 5 is on innovation in education. And we have 5 10-minute talks lined up. And the first talk is from Anne Buckner from the University of Exeter in the United Kingdom. And I see you are there. So your talk is a whole lot of fun explaining astronomy with 3D holograms. So welcome, Anne. You have 10 minutes. I will give you a warning after 8 minutes. Is that okay?
Thank you. I'll just share screen. Oh, that's odd. I don't seem to have an option to share screen.
There should be a green box at the bottom with an up arrow.
Okay.
Which you click and it should then
it doesn't, it opens a box, but it doesn't have anything in the box. That's odd.
No, yeah, you click on the green box. It's for everyone the same, I think. I don't know which is what version of Zoom do you have, but it's the same anywhere. And you have all the permissions, so you can share the screen and the camera and so on.
No. I'm very sorry, but I don't have the normal button that allows me to choose desktop or a window. This is very odd. maybe someone, the next talker, maybe first, while I try and sort this out.
Yes, John, I propose the next speaker, and meanwhile I will talk in private with Anne and try to solve this situation.
Thank you.
All right, so shall we go on to the second speaker, and that is Priya Hasan from Hyderabad in India. Are you there, Priya? I saw you were logged on earlier. Well, there's your PowerPoints. And can you turn your camera on? I see your PowerPoint, but not you.
1 sec. I'll just. I've been having. Okay,
I saw you
did
then.
You see it?
Yes.
Okay.
So
can you see me now?
I can.
Okay,
yes,
good.
We can see you. We can
Priya
see you.
Hasan is from the Maulana Azad National University, Hyderabad, India, and she is going to talk about astronomy, data, the virtual observatory, and education.
Yeah. So thanks so
Priya,
much. Thank you, John. Yeah. Thank you, John. And,
I give you a warning after
everyone.
8 minutes, starting now.
Sure. So, hello everyone, I'm Priya Hasan from Maulana Azad National Urdu University, which is located in Hyderabad, India. And being from the teaching community, I'm sure all of us who are there from the teaching community have realized that this truly has been a year of innovations, right? Nobody had ever dreamed of such a situation which actually came in with the pandemic. And some of us had done some amount of virtual teaching, but I think nobody had done it at the scale at which we are doing it in the present times, right? I teach physics and astronomy, and we're actually even doing physics labs online, which is actually weird, but we do it. And this is actually a work which we've been doing. We have a small organization called Shrishti Astronomy. And the project I'd be basically talking about is a project which has been funded by the IUOAD, which was specially for COVID times. And this project has also been supported by the IBOA. And I'd like to thank all of them for that. So what happened? I don't, okay. I think I have a, okay, yeah. So what happened is when the pandemic started, initially, we started off doing some amount of outreachy kind of things. So the first thing which we actually tried doing was a 6-day school on astronomy, where we actually had online astronomy classes. This was way back in May, where we covered some basic topics in astronomy, where people could ask questions and interact, and we covered some basics. We also tried to do a workshop on physics at home. That is, we actually took up the broad areas of Newton's laws, gravity, simple machines, pressure, optics, electricity, magnetism, and using certain kits we had at home with things we could manage, we tried to use that to actually demonstrate some physics experiments. This was for school children, for essentially high school children. And that's how we started off. And after that, what happened was the IAU, Office for Astronomy for Development, came up with a call for COVID-related proposals, where it was meant for a six-month time period, where you could propose a project. And we actually proposed something called Astronomy from Archival Data. And essentially, the idea of this project was we could actually see that our students, most of them were very upset because they were stuck at home and they could not be doing work. A lot of them are the ones who are, interested in joining for a PhD program. And there's a lot of outreachy things available for people online. But many of them actually were looking for work where they can actually do some kind of research and some kind of, active, this thing which can be used as part of their proposals for PhD applications or some kind of exposure to research. So this basic proposal, this basic project was aimed at that. What we actually did is we kept an online call, and actually I'm sure the number has got revised, but sometime back we actually had 915 responses and students from more than 23 countries. And that was clearly an indicator that this is exactly what students want, right? There's a large number of students who actually want this kind of stuff. So, oops, sorry. So, yeah, here's my team. My team is a home team. That's my husband over there. And what we do is together we actually have been doing our things. So he also works in mathematics and astronomy and more physics and astronomy. So this is our joint, we do this joint kind of stuff. And this is a picture from one of an older telescope making workshop, which was done earlier. And what did we do basically in this? What was the modus operandi? We basically used Zoom and social media, along with telegrams, emails, etc. And we basically, used virtual observatory tools to teach students virtual observatory tools, as well as expose them to the amount of archival data that is available, because that is of the best quality and there's so much more one can tap and get from that data. We also made it a point to include a variety of speakers for our talks, which ranged from, Mark Taylor, who wrote the code for TopCat, Louisa Reboul, who works with IPAC, Bruno, who's in ESA, and a few Indian friends, etc., who actually all helped us to make the thing more holistic, as well as, covering a larger range of areas, because otherwise it would only be limited to the areas that we are familiar with. So we got all these people to do. So the concentration was on doing VO tools, first of all, and then also discussing research problems which students could do. So we actually started this thing, the session started in the 1st of August, and we just completed it on the end of November. So we had sessions on Saturday, Sundays from 10 to 11:30 in the mornings for 4 months. So we have more than 60 videos already available on our YouTube site. Since there were students from so many different countries, not everybody could log into Zoom at the right time. So they could then access it through YouTube and put in their questions, etc. over there. We made a website and all that, where you have all the details about the sessions, the reading material, the homework, the quizzes, the software, etc. And we were constantly even taking feedback from students to know what do they feel about it. And so the idea was to do this on Saturday, Sunday mornings, because gradually throughout the world, the academic programs had already started in universities. It was for us too. We already started teaching classes. So the idea was to take a period which is free for the students. It doesn't clash with their regular things, as well as make the recordings. All the recordings are available so that students can watch them whenever they want. Since we had students from so many different countries, there was just a talk about English domination. So we actually had we had students from Bologna and, a lot of South American countries too. So what we did was very simple. In YouTube, you can just enable subtitles. So the students could actually watch the videos very comfortably with subtitles in the language they were comfortable with. And but still, especially in India, a lot of students had issues, for example, with network, with power, etc. So the fact that the videos were available all the time was good, so that students could access it whenever they had network availability as well as power availability. So here's a picture of one of the Zoom sessions we had. So we had the Zoom session where we only had funds for 100 participants. So the rest of them could log in from YouTube. And this is, I think, the Mark Taylor session where you have all these things. And we also encourage students to interact and speak with the, talk, interact and all that. The YouTube channel, which we set up, this is some days back. I already have 461 subscribers. We have a whole lot of videos available over here. Like I said, we already have 60 videos over here where we covered things like, tools like AstroPy, Python, big data, machine learning, and, so the ESA Sky, Aladdin, TopCat, all these kind of things, as well as then there was discussion on proper research problems. So that was phase 1 of the project, which we've just finished. And now phase 2 is
Priya.
where we have proposed projects which students can take up. Yeah. So students can actually take up the projects and actually do their projects. So students are now already doing their projects, which they will present in the second half of January. And that's when we finish our whole thing, which will be the end of January, after students visit this thing. So here's an example of one of the Zoom sessions which we have, and a lot of these things. So this is a picture from the website, which actually has a lot of details. I'll put the website on the chat window. So please do have a look at it. And like I mentioned, we've used various data sets from Gaia, HSD, Tuma, Spitzer, Chandra, etc. A whole lot of data sets. Like I mentioned, there are a whole lot of tools also, which we covered. Python, AstroPy, TopCat, Aladdin, R, machine learning, big data. The science cases also varied from Gaia to SDSS, Kepler, magnetars, galaxy morphology. And the good news is that we have another project now from OAD, which is called Astro Sprint, which is for the whole of 2021, where we are actually planning 3 workshops with everyone. Some of them would be the participants, and new ones are also welcome. So probably the first workshop, which will be in March, will be virtual. But after that, we hope that the next 2 workshops, one in Jan and one in November, would be face-on ones where we can actually offline meet participants and continue with the work that we did in this project. Thanks a lot. Thank you. Thanks, John. I'm done.
Okay, excellent. So thanks very much for a wonderful talk. We're going to move straight on now to the next talk, but we'll come back if there are any questions after the 5 talks. So don't disappear. Anne, are you back and able to present?
Yes, I'm going to try again, but Beatrice has my presentation if this doesn't work again. So, so she'll share her screen. So, okay, yeah, indeed, it's still not working. So, Beatrice, could you share my presentation on your screen, please?
While Beatrice is doing that, shall I just introduce Anne again? She comes from the University of Exeter in UK, and her talk is a whole lot of fun explaining astronomy with 3D holograms. So, Beatrice, can you bring her PowerPoint up? You're muted, Beatrice.
Thank you. I will share my screen with everyone again.
Thank you.
Now you are welcome. Let me see.
So you'll have to do the advances of the slides.
Please let me know if you can see the slides.
I can.
Okay.
Okay, so today I'm going to be talking to you about using 3D holograms for explaining astronomy in an outreach context, and I'm going to give you a pandemic friendly guide. Next slide, please. So first of all, I'm going to talk to you about what are holograms, and then I'm going to talk to you about how I've been using them pre-pandemic, how I've been using them in the pandemic, and how you can use holograms for your outreach. Next slide, please. So holograms are essentially just a optical illusion. They are a 2D reflection of light off a surface. but your brain interprets the images as a 3D object. Next slide, please. So it works by, you have a screen such as a TV or a tablet, and you have something called a hologram projector, which is essentially just a pyramid, plastic pyramid with that's placed in the center of the screen. The images then reflect up off the surface of the pyramid, but the way the brain works is your brain tells you that it's not a 2D image on the surface, that it's actually a 3D image inside the pyramid. And because you can see it on all sides of the pyramid, your brain, that just reinforces the idea that the hologram is actually inside the pyramid rather than on the surfaces. Next slide, please. So pre-pandemic, what I was doing was high school astronomy outreach. My research area is star formation and star clusters, so I was using it to explain that to the kids. What I would do is I would do a 1 hour workshop, in-person workshop with them. So I have these very large hologram generating devices using 60-inch and 32-inch TV screens, which make holograms like the size of a soccer ball or cricket ball, depending on which size they use. And I would do that, I would do a tandem PowerPoint presentation like you're seeing now, and then I would also show them these holograms as part of the presentation. Next slide, please. So why was I using holograms? So they're very, very visually engaging. You can get students that have absolutely zero interest in astronomy and do not look like they're about to be bored and out of their mind and have water torture done to them. But suddenly come and be like, oh, I'm excited because, you know, it's holograms are, it's not so much the astronomy, they're just very excited about holograms, and you can kind of like bring them into astronomy through that. And most importantly, it brings very abstract ideas in astronomy to life. Next slide, please. So, for example, the sun is in fact an abstract topic. I know it probably isn't to most of you, but I promise to 11 to 18-year-olds it is. Most of them have not given it a second thought. To most of them, it is just something that's there in the day. That's it. So the idea that it's a 3D object, it's burning gas in space, it rotates, there's like flames coming off the sides or like surfaces, is quite an abstract idea. So the fact that you can have a 3D sun rotating in a hologram showing all these like prominences and stuff is it really helps them to understand. Next slide, please. For example, I'm in star cluster evolution, so explaining that star clusters go from the left-hand image, which is about 5 million years old. So the stars are kind of scattered over the cloud, gravitationally bound, but not in any particular shape. But they change their spatial configuration over millions of years to become more of a ball-type shape, like the image on the right. So what I can do with holograms is, and simulations, is have a hologram of a star cluster, and then the stars all whizzing around and evolving over millions of years. Next slide, please. Then the pandemic hit, and things you can do in a pandemic. Next slide, please. You can still do your high school astronomy outreach. You can still explain star formation, but the in-person group workshops are out. Next slide, please. And virtual workshops are in, which kind of posed a slight problem, because the whole point of holograms is that, you know, the kids can like walk around and see them. If I just did a hologram via video link, that's no different than doing a 2D video, so I had to give it some thought. Next slide, please. So when I came up with the idea, instead of me showing them one giant hologram, that every kid could make their own mini hologram projector that works with a tablet or a phone, so then I would give a virtual talk and they could watch the holograms on their phone. So the first step is to create the hologram videos, which you would do for the in-person workshop anyway, but then I upload them onto YouTube and send links to the participants, along with a free template on how to make one of these for their phone or tablet. Then before my talk, that the participants will then make one of these, and then I give my talk, I'll give the PowerPoint presentation when screen share works, then I would say, okay, now we're going to talk about the sun, so I'd bring up the sun hologram, and they would bring up the sun hologram on their phone. A concern I had starting off was, you know, we've gone from this awe-inspiring giant holograms to like these smaller holograms. Will that take away some of the, like, you know, the intrigue? But actually it's something quite magical to the kids, that they can hold like mini suns and mini Jupiters in the palm of their hands. They really like that idea. Next slide, please. And here's some example feedback I got in the post from a virtual workshop I gave a few weeks ago. As you can see, they're like, oh, thank you. I love the holograms. I enjoyed the visit. Extremely interesting, intriguing. So they really do enjoy this idea of holding like little models in the palm of their hands. Next slide, please. And next slide, please. Yeah. So you don't really need any budget from which to do from your own outreach. All you need is a photo or a video, either from your own research, or NASA and Hubble have free ones. And then just a free video editor, and there's a link on the last slide of a tutorial on how to do it. And then all your audience will need is the hologram template, project template, which you will send them, and it's free. A phone or tablet, everyone has one of those. Scissors, tape, pen, again, people have those. And then some kind of clear plastic, such as like projector sheets or a CD case. Everyone can probably find scrounging around their house at least something which to make these little devices. Next slide, please. So to sum it all up, holograms are a great outreach tool. They're very visually effective and engaging, and they really do spark the imagination of students and bring the abstract ideas to life. They can really pull in students that aren't interested in what you're going to say into making them actually interested in what you're going to say. I've got great positive feedback from both in-person and virtual workshops, so that works. And very simple and easy to make the hologram videos, and no budget is required. Next slide, please. So if you have any questions, please feel free to email me. And then there's a 5-minute tutorial that if I can do it, anyone can do it, because I had no video editing experience prior to this, here on this link if you are interested in trying out holograms for yourself. So thank you.
Well, that's fantastic. You finished ahead of time, so congratulations. You could speak for another 1 or 2 minutes, but if you said all you have to, that's great. Thank you very much.
Thank you. Bye.
So let's go on to our third talk of this session, and that is from Travis Rector in the University of Alaska in Anchorage, Alaska. Are you there, Travis?
Yes, hi, I'm here. If you can make me a co-host, then I can turn on my video and share my screen.
Give me a moment, Travis, because I cannot see you in my list. Sorry. Wait a minute.
Okay, please. Look under the letter T.
Yeah, sorry. Yeah. Now, try now, please.
Okay, it looks like it's working.
Okay, so Travis has a talk on using real data in the classroom to teach the process of science. Travis, you've got 10 minutes. I will give you a warning after 8.
Okay, thank you very much.
Go ahead.
Hi, everyone, and welcome from Anchorage, Alaska, where it is 3 a.m. But hey, we're astronomers. Being up late in the night is what we do. So I'm going to talk with you about what are called CURES, which is an acronym for Course-Based Undergraduate Research Experiences. And what these are is an opportunity for your students in your introductory science classes, whether they be at the high school or college level, to be involved in an authentic research project where they will analyze real data using research quality tools. And the goal is for them to work on questions for which the answer is not yet known. So for example, we're not asking them to calculate the orbital period of the Galilean moons or do something that is already known to a high degree of accuracy. So how does CURE fall into the spectrum of different learning contexts? Well, in a traditional astronomy class, there is very little practice of science itself. And so students learn science as being a static body of knowledge, and they don't learn that science is the process by which we actually do create knowledge. Now, many people know about what's called inquiry-based learning, where you simulate the research experience. You may give them real data and real tools, but what they're doing is still limited to the relevant is to the course themselves. It doesn't extend beyond that. So in a CURE, they do real research, and one of the goals is for what they generate will actually go on and be published in some capacity and increase the knowledge that the world has. And so one of the goals of this is to teach that science is a process. It's not simply a static body of knowledge. and to help generate critical thinking skills, and also to develop positive attitudes towards science. That is, to get people interested in either wanting to be scientists or go into a STEM career, or even just have a better attitude, a more positive attitude towards what it is that scientists do. So over the years, we've developed many different projects. We currently have 5 running in some capacity. And for each of these projects, we have developed a documentation and the software and the data sets needed to get students up to speed so they can participate. So I'm going to describe to you one of the projects, which is a search for near-Earth asteroids that might have the potential of hitting the Earth someday. So we have various tools like Orbit Master, which is designed to show the orbits of asteroids, and this is based upon the JPL Orbit Viewer, but we have added functionality that allows students to learn and better understand what orbits are. So in our project, we're doing what are called recovery observations. When an asteroid is first discovered, we don't know the orbital parameters very well, and so over time, the uncertainty as to where that asteroid is will increase to the point where it will no longer be you'll no longer be able to find it. So it's very important within the first few days of its discovery to do follow-up observations. And so what we do is follows this circular path, which I'm going to describe just very briefly. So we start off by going to the IAU Planet Center and looking for near-Earth objects that have been recently discovered and have a high uncertainty and are in need of follow-up observations. We then find targets that are within the right ascension and declination range for the time range that we'll be observing. And then students schedule the observations into the Skynet Robotic Telescope Network, where they put in the name of the object. And fortunately, Skynet is clever enough to be able to calculate where the telescope should point at the time the observations are executed. And we do this all with the Yerkes 40-inch or 1-meter telescope, which is a good size for being able to find modest-sized asteroids. And then once the data are taken, students go through the observations and they look for a dot that's moving. And if you look closely here, you'll see that I'm stepping through 3 observations, and you can see the asteroid that's moving at the center. So one of the things students do is they calculate where they thought the asteroid should be and then measure where it actually is and see that it's different. They then use a program called Find Orb, which is short for Find Orbit, to calculate a more refined orbit. And in particular, they do what are called Monte Carlo calculations to determine the range of potential orbits for this particular asteroid. So before students do this, the range of asteroids may be very large. And in this picture, you see the green circles represent 500 different possible orbits for a recently discovered asteroid. But after doing their observations and combining in other observations as well, they refine that down to a much more precise region. So as part of this, they learn that much of science is the refinement of knowledge. It's not just simply the eureka moments where people like Einstein and Galileo make radical discoveries. Now, the most fun part about this is that the students submit their observations to the IAU Minor Planet Center, and then within a month, they're actually published in the MPC circulars. So within the time span of the course, they're able to see that what they've done has had value. And so they can see that they've added knowledge to the overall scientific community. This isn't just simply an activity that was in their class. So what are some of the benefits of doing CURIOUS? Well, we've done a variety of studies over the years, and I'm just going to describe a few. But one of the things we've done is use concept mapping to see how participating in a CURIOUS changes their understanding of the process of scientific research. And what we have found is that students make improvements in understanding that science is based upon prior knowledge from previous research, and that the information they generate will go to inform the next round of knowledge generation. Now, they've made the least improvement in understanding the data collection process, which makes sense because they're not actually doing it. Even though they do schedule the observations on a robotic facility, they aren't actually obviously there to collect the data, and they're not part of the data reduction process. They just simply do the data analysis. We also found that students made significant gains in their confidence and ability to do science and also their trust in the work that other scientists do. So what are the biggest barriers to the implementation of cures? Well, the first and foremost is a reliable source of data. If you're going to use real data, you want to have data that is of research quality that can be used for the sorts of projects that you want to do. Now, in the case of our asteroid project, we needed observations that are fresh. So we couldn't use observations that may of a particular region that were not at the time that the asteroid would be there. So that's what's really exciting about projects like the Vera Rubin telescope, where we will have a continuous stream of new data coming in every night that can be used for new sorts of projects. Another major barrier was the difficulties we had with software and data. That is, nowadays it's very difficult to have students install software in their own data set. And so one of the things that we and other groups are doing is moving to an entirely online experience that just works through a web browser. So there's no installation of software, there's no downloading of data sets. Everything can be done just simply through a web browser interface with something like HTML5.
2 minutes, Travis.
Thank you. And then finally, one of the biggest issues is instructor confidence in doing the research projects. And so as teachers, we often feel like we need to understand something to a high level of expertise before we're willing to teach it. But in these projects, what we're really doing is we're collaborating with our students. So you don't need to be an expert in asteroid research. I certainly not. My area of research is star formation. But if you know enough that you can help your students work through the project, then you work more in a collaborative role than as the sage on the stage. That is the expert who knows everything about it. And it actually makes it a lot more fun for your students and for you. And it's a much more accurate representation of actual research, since after all, when we do authentic research, we don't have someone that we can contact to tell us if we've necessarily gotten the right answer. And so those have been the largest barriers from implementation. So thank you all for listening. I hope you've enjoyed. In the comment section, the chat session, I'll type in the link to our websites where people can actually download materials. Several of our projects are available so that people can go ahead and participate on their own. So thank you very much.
Thank you, Travis, for that interesting talk. And you also are slightly ahead of time by about 10 seconds. So thank you very much for that.
Precision is very important in what we do.
Absolutely, yes. And you have excelled in being precise. So now our next talk, we've got two speakers, and I hope I pronounced their names correctly. Ilhuiyolitzin, Villicana, Pedraza, and Francisco Carreto, Parra.
Okay, thank you so much.
Yes, you're both there. And how do you pronounce your name, can I ask?
Yes, Ilhuiyolitzin.
Good. And she is from the Doña Ana Community College at the New Mexico State University, and Francisco is from the El Paso Community College in Texas, I believe.
Yeah, perfect.
Good.
Thank you so much.
You have 10 minutes and I will warn you after 8. Please go ahead.
Perfect. Thank you so much. Well, first of all, I want to okay, yes, this is my topic, real data for astronomy classes in the college and university. I have been teaching around 8 in different types, different periods, 8 different periods for online classes and 10 periods for face-to-face classes. So I use this information for both classes. I am, as he told, from the New Mexico State University. I belong to the physics department, and then from the college for the science departments. Okay, and oh, sorry. Okay, okay. Then, I want to tell here that one of my motivations to be astronomer was the classes with Julieta Fierro. It was amazing. So now I am astronomer. Then, well, as introduction, the correction dissemination of the astronomical material for college students during their classes will help to engage the students selecting the STEM majors. But sometimes the students don't choose STEM majors, but we need to be sure that they love astronomy. If they love astronomy, they will participate in the future in their works, they will support astronomy. So this is very, very important. Then, I designed some labs for my classes, all my classes I teach Astro 110, this is Introduction to Astronomy, and also the planets, this Astro 15. And then I designed analysis of professional astronomical observations. This is the last lab of my classes. And then the first that I did is about exoplanets. It was, the first one was in 2017. With this, I did characterization of exoplanets with Kepler. And then I know that it's very easy. We can use the catalogs that are public. Then basically the objective of this lab was learn how to analyze the scientific information from the literature and create tables and graphics to compare exoplanets with planets of our solar system. So the students can visualize better and compare what are outside and inside of our solar system. Here is the paper that I use. They need to create tables. The first table they need include the temperature, the effective temperature, the radius with respect of the sun, and so the identification of the planets, the period in days, the radius of the planets, and in which star is associated. And then also they create a plot like this, and then they can find a way to describe this kind of plots. Then also in 2018, I found another another lab that is very interesting. This is again like the past talk about asteroids. Then the objectives for this is find a relation between the diameter and the rotation period of the asteroids. I am using NEOs and asteroids that belong to the main belt. And then the students create the light curve. Because we observe, well, we use the photometry database. This is the page. And then also it's very important that for me that they know which asteroids are hazard and which not. Because, you know, in the news, they say, one asteroid will hit the Earth the next month. And then always the people and also my students, teacher, this is true? No, it's not true. And then I always send to my students to check the space weather page, and then they need to create a table to know the name, the distance, the velocity, and the diameter, so they can identify which asteroids are the most dangerous for us. And then they finally conclude that they are not really hazards for us. Then this is an observation. I have a synergy with the main campus, with astronomy departments, and then this observation and analysis with the Tortugas Mountain Observatory. This is a 60 centimeters observatory. It is a project that we have since 2019. And then, well, here all the people that is involved. And then we have observations. We observe some planets, asteroids, galaxies during 3 days in remote mode from the classroom. And also we use different filters like blue, visual red, infrared, and H-alpha. Each asteroid was observed at least 2 times using all the filters. And then time exposure, well, between 30 seconds, 60 seconds. The students take the observations, take the data. We teach to them how to do that, because it's very important that the students feel the real thing, that what one astronomer is doing. This is like a small proof to check what is a real astronomer doing. Then the idea, well, for example, one of the things that we did is search the asteroid Mayal by comparing the observed image obtained, just like the past talk that we check like a video or something like that. We check different images that we observe, and then we can find where is the asteroid. Then after that we find it, we use the DS9 to compare the image with all the filters, and then also we analyze it with the MPO Canopus software to do photometry, and then we obtain some points that we can use to do a light curve. But of course we have 2, 3, 4 points for the light curve, so we need to complete the light curve with the database for asteroids in this page. And finally the students can do a plot like this, a light curve, asteroid Mayar, and then also with the same observation, because we observed also planets, they can do this kind of things. They can practice with the GRB colors using DS9, and then they can see the difference. This is the telescope. Then also we use the Sloan Digital Sky Survey. It is since 2019 because NMSU, the university that we are, is the home of the data for the Sloan. So we had a workshop and all that, and then we use the information with the students, and we use it for the spectroscopy lab with the SDSSS observations. We use the Sky Server DR16 plus the DSSS to find the spectra from one disk or the spectra of the plates. The students identify the features, like you can see here at the right, the first image. Here's the link. And then also we know, because you have the plates, and then the plates, they have holes. And then each plate, each spectroscopy plate has either more than 600 or 1,000 of spectra. They have like fibers. And then they observe simultaneously all the fibers at the same time. So we have a lot of information with these plates, and the students can use it to use the parameters that you can see in the second and the third part here. And then we are in the first, we only choose, this is, of course, you can, it is public information, and then we use a plate and the fiber, and we obtain the spectra. And then in the second, in the second, the students only check the information and then they can use it. Then also, we are user testers for the Vera Rubin Observatory as teacher and also for students. And then we have, for example, in my case, I had 24 students for Astro 1.5, and for Astro 1.10, other 24 students. Here are the topics for Professor Carreto. He has 30 students. And then this is very, very interesting. Around 70 to 80% of the students work correctly with the information and learn much more. The innovation, the city in the space, explain to the leaders. This is a project that I did from this year in summer and then also in fall. And then the city space is an imaginary city in the space, and then they can say what can they do with these skills. And the other is searching of the habitable planets. And then basically this is the concept. They need to search for this, for the class of stars and galaxies. And then that's it. I have here all the information if you have more questions. Thank you.
Okay, so thank you very much. That's exactly on time, so that's perfect. Thank you for your talk. And now we have one last presentation in this session, and that's from Fraser Lewis, National Schools Observatory Faulkes Telescope Project in Wales. Fraser, are you there?
I'm here. Do you hear me?
Yes, and I can see you as well.
Fantastic. So we're almost there.
IBSE-Type astronomy project using real data.
Yeah.
And I see IBSE means inquiry-based science education. Is that right?
That is absolutely correct. Thank you for putting that one in for me. That's one less thing I need to explain in my talk.
Well, your 10 minutes starts now.
I'm going. Okay, yes. So I'm Fraser Lewis. I'm based with the Faulkes Telescope project in Cardiff, and also the National Schools Observatory, which is based up in Liverpool. And you'll have seen a talk, hopefully earlier this week, from Sally Cooper, who explained quite a lot about what the National Schools Observatory does generally. So I'm very lucky. I work with two different projects, each of which have access to 2-meter telescopes. And we kind of know that telescopes, in a sense, bigger is better. And I have access to the 2-meter telescopes in Australia and Hawaii that are part of the Faulkes Telescope project and part of the broader Las Cumbres Observatory network, and also the Liverpool telescope. So we're very lucky.
Can you move your camera so we can see all your face?
I'm sorry. No, I hide a lot.
Much
so I do
better.
apologize.
Thank
there
you.
you go. Okay, I'm all encouraging. Okay, so there we go. So that's sort of an indication of the telescopes that I have access to. I should say that as teachers, you also have access to these. This is the key point of the talk. It's not about me telling you what I can do with the telescopes. It's much more about telling you what you and your teachers can do with the telescopes. That's much more important. I hope we agree with that top statement. If we don't agree with that top statement, we may be in the wrong conference. I think astronomy is very, it's a lot of fun. It's a very good thing to do to inspire people. We struggle sometimes to put it in the curriculum. We struggle sometimes to find it in the curriculum. But we're resourceful people. We become multidisciplinary. We think about maths. We think about IT. We think about chemistry and biology. And obviously now we also are starting to include the A from arts into STEM to make STEAM. And another thing we can do very well in astronomy that we really want to pursue, both the projects I work for trying to pursue this, is to encourage the schools to collaborate with each other. And if we can do that internationally, I think that's a very reasonable thing to be trying to do as well. On that basis, one of the projects that I've been working with for a while is using the Gaia data. So Gaia, if you don't already know, is a European Space Agency mission. It's mapping our galaxy. It's understanding something about the shape and distribution of stars in our galaxy and the evolution of the galaxy. It has that strapline of 1 billion stars for €1 billion with a 1 billion pixel camera. There are some web links there that you can pick up as well if you're interested in finding out more about Gaia. Part of the work we've done initially with the Faulkes telescope was to design lots of background material, lots of sort of worksheets based around what Gaia does, not just the astronomy, but the technology, the engineering. Where is it based? Where does it get its power from? You know, its launch, things like that. So again, there are web links there to the kinds of resources we've produced there, which I should credit one of our postgrads at the time, Sophie Bartlett, for, rather than staking claim on that myself. As a result of that, and working with the Gaia alerts people, so looking at transient sources, things like supernova within the Gaia alert stream, we've been lucky enough to get students onto papers. I think this was something that was being mentioned 2 or 3 times in this session alone, that if you can get students and teachers onto papers, and this is an astronomy and astrophysics paper published earlier this year, and legitimately on there, not just on there because they happened to be passing when we were doing something, but actually taking data and being involved in that process. That's really important, really nice thing to be able to do. Moving on to the IBSE, the inquiry-based resources that I've been able to produce with my sort of project mentor, my manager in Liverpool, Andy Newsom, who I know is listening somewhere. We have designed these to be teacher-free. I take a bit of a gulp when I say that because it feels like I'm trying to do teachers out of a job. That's not what we're here for at all. But we're designing standalone resources that are online to look at things like the HR diagram, how stars evolve. We've heard the HR diagram mentioned already today as well. Here we provide data sets, so existing data sets of different open clusters that the students can use software, in this case Macaulay, which is created by the Japanese astronomers as a free download package. We provide all the instructions, all the data. What we want to encourage at the end of that is the students to go off and take their own data. Ownership of data is a really nice thing for the students to have at that point. A second one that we produced is on exoplanets. So again, in this sense, we're not taking data from our own telescopes, but we're looking at population studies of the current known exoplanet systems. And we provide lots of instructions here on how to actually analyze that data, to look for trends in there, to look for clumps, modality, things like that, and also those selection effects that come in that fool us sometimes. The third one that I wanted to mention today, and I appreciate I'm flying through these, but it's really just trying to give you a flavor of what we've been able to do. This is dipping our toe into the citizen science world and thinking about supernovae. So there's actually a very interesting link, as most of us know already, between type 1a supernovae, stars that explode in our galaxy and in other galaxies, and the expansion of the universe. It's a very, very, there are a few steps along the way, but this is work that created Nobel Prizes in the last 20 years or so. So we're following on that type of information. So again, we provide data. Here we're using an online photometry tool. So we're not using Macaulay or Salsa J or any of those photometry tools that exist. We're playing around with a thing called JS9, which is an online version of DS9. So we're trying to remove that sort of problem that people have with platforms and downloading software and so on. This is a very convoluted set of steps, which we hopefully guide students through, where they can use Excel sheets, they can use sample data that we know will work, and then go off and collect their own data, again, providing them with ownership of their own data. This, we think, gives us a chance to provide the students not just with knowledge of type 1a supernovae, not just with knowledge of the universe, but to gain a feel for what the scientific process is about, to reflect on their work, to collaborate. Some of these data sets are very large, and it drives you absolutely crazy trying to do several hundred data points. But things like Google spreadsheets means we can share the workload among students. Those students don't even need to be in the same school or the same continent. We find lots of things in maths that we don't like, such as periodicity, trend lines, logarithms, error bars. These are all things that we use in astronomy, and we can sneak them in. We can sneak in that maths by using astronomy, and we can allow the students to sort of think about how they extend these projects. I think it's fair. I think it's only fair to mention the hurdles and problems that we've encountered along the way. I don't think any of these things that we've spoken about today come without problems along the way. But there are things that we're trying to do. We understand that teachers and students particularly struggle to install software. So this is why we're looking at JS9. We know also that students don't like the idea of finding out that the answer is not 12. We don't want that single answer. Yes, it's correct, off you go. But that, astronomy is an evolving field, and we're still understanding things as we go along. We want students to use their own data, but their own data sometimes is not as good as the sample data sets that we know will work. And, again, the timescales from doing some nice science to actually getting that science published in professional sense often takes 1 to 2 years. And that's not a great timescale for inspiring students, as we know. I'm going to jump across to one more thing. John hasn't told me I've got 2 minutes left yet, but I'm conscious I probably have about 2 minutes left or so.
You have 2 minutes left right now.
Fantastic. We're going to do this on time. We get everyone away for lunch or sleep or whatever. This is the very first time I've had a chair who I need to try and make sure stays awake through the entirety of my talk. I wanted to mention this one because there's been a lot of talk this week about languages and why is everything in English. And we're very lucky in the English speaking world that that's the case. We're not the best language students very often. This is a project that I've been working with the Faulkes Telescope project, which is provided in lots of different European languages. I won't list them, but if you have a look on the website, you'll see them, but it is all the major European languages. Looking at things like comets, meteorites, and impacts. You can create your own asteroid. Again, it has this inquiry-based style to it. Here is a screenshot of what you may produce, which is that you design your own asteroid. You crash it into a randomly selected part of the Earth, which just on this occasion happens to be Washington in the US for no reason whatsoever, but let's assume that's okay. But this is a nice example of again, inquiry-based. It's suitable for kids of lots of different ages. It talks about what meteorites and meteors and asteroids do to the Earth, how that links in with the death of the dinosaurs, which kids love because it's dinosaurs and death. What better piece of science could you ever give them than that? I think, John, that's me pretty much done. I will leave you with my details. Encourage you to have a look at those resources. And if you have a feel for any inquiry-based science education resources you would like, contact me and we will see if we can work on something with you. Thank you very much for your time and your attention.
Thank you so much, Fraser. So that's also on time. I've been extremely lucky that all my speakers have kept to time without me cracking any whips. So that's wonderful.
Very much a rarity for me, I can assure you.
Yes, well, I'll take your word for it. Now, Beatrice, can you help me? Because we're meant to have 10 minutes for questions, but I've opened my Q&A box and I don't see questions there.
No, at the Q&A, there are not questions, specific questions, but there are some at the chat window. Well, I must follow this. Well, what time do you start? Because the idea is to go to the beginning, 9:30 here. Okay. Well, I have one question or suggestion for Travis. The confidence of the instructors and the protagonists can be increased by setting progressive goals in ambition. It is not a question, it is a kind suggestion from Claudio.
Thanks for the suggestion.
Okay, are you there? Turn on the cameras, the speakers, please. Yes, Nicolas.
I think that there's a nice question from George Soti to Anne that it's already answered by her, but I think that it's quite nice to answer Liv, that it says, the hologram is nice, but it's not rather a Pepper's Ghost. How truly 3D are the images?
Yeah.
So it's kind of all an optical illusion. For those of you not familiar, Pepper's Ghost is an old magician's trick, which actually inspired the holograms, where you kind of reflect an image off a surface, and therefore it appears to be the reflection of, like, so you would reflect an object of a person and say it would look like a ghost on the reflected surface. Because this is a pyramid and you get the same image at the same time reflected on all four surfaces, this kind of adds to the optical illusion that when you walk around, your brain tells you, oh, I'm seeing it from all sides, it must be in the middle. In addition, while it's not necessary to make a hologram, what I do is I make perspective on my holograms. So for example, if a star is moving around in a cluster and it comes towards the person, the star gets bigger, and if it moves away, it goes smaller again. So in that way, it adds to the 3D illusion. But yes, the actual images are not three-dimensional. It's not like a Star Trek style hologram, but it's all an optical illusion, but it works quite well to trick you into thinking it's three-dimensional. So.
Here are one question for Travis. In the process, you evaluate mental map, pre-post, is from Sarah Richard. It was made by Sarah.
So yes, we do pre and post concept mapping on a set list of concepts related to scientific research. And what we're interested in doing is seeing how well they are able to connect the different components to scientific research. So we measure gains from pre-post maps.
Okay, I cannot see. Nicolas, help me also, please. And well, I think.
Yes,
I see lots of stuff, lots of chats, but no questions. Is that right, Beatrice?
Yeah.
Maybe one more to Travis that he already answered in the Q&A section from John Briggs. That maybe it's interesting to say something more. That it says, do you find that Skynet is sufficient for your observing needs, or is it likely you'll need additional observing resources, for example, because of the current closure of JERGs? Your excellent asteroid project reminds me of what is done in the annual summer science program for high school students. So maybe something further.
Yeah, so unfortunately the Yerkes telescopes are closed right now. Hopefully they will reopen soon. But I'll just let people know that for doing the asteroid project, ideally you would have a 1 meter class telescope or larger. We find on any given night there's about 12 to 20 asteroids that are in need of recovery observations that are accessible by 1 meter class. As you start getting to smaller telescopes, there's fewer and fewer asteroids available. And basically, a 0.4 to 0.6 meter telescope is the smallest that you could hope to be able to find asteroids that are bright enough that you could do the project with.
Okay. I cannot see more questions, John.
So shall we close session 5 now, Beatrice?
Yes, of course.
And it is approximately on schedule. We started a few minutes late and we're finishing a few minutes late, but not too much.
No, at all. Very good in time. Now is, yes, thank you very much. Thank you very much, the speakers, the presenters.